All right. Hi everyone. Crispus Ben Boyo is my name, and I'm the presenter right here of the explainable machine learning techniques for predictive car engine health monitoring. We shall straight away move to our introduction. Um, where we shall look at we have the introduction, related works, problem statement, research objectives, and questions, contribution, methodology or system architecture, dataset description, experiment or simulation results, conclusion, limitations and recommendation, references, and then acknowledgement. Straight away to our introduction, we have the tech advances one, where we shall use the sensors. Sensors are basically devices that detect and measure physical conditions and then represent them in a way that an observer can understand. Now, edge computing is a technology that enables us to process data next to the source. And the main importance of this is one is to improve speed and lower latency issues. The current challenges that we are trying to address are one, the absence of the real-time diagnostics. Now, this is basically the instant detection and analysis of problems as they occur. Now, and moving on to the traditional methods, this is basically an old way of doing things before modern innovation. And the solution we are presenting to address these challenges are one, a predictive analytics system. And this is a system that uses statistical algorithms and machine learning techniques, as well as data to predict trends. Engine health is basically the well-being of an engine, and then real-time diagnostics, I explained it area instant detection and analysis of issues as they occur. Now, machine learning algorithms are just tools that help computers to learn from data and then as well predict or make decisions. The benefits of the solution that the predictive analytics system we are introducing is one is to reduce the unscheduled breakdowns and as well as improve vehicle reliability. The potential impacts are one, predictive maintenance. This is basically um, detecting and addressing issues before they what? Before they occur. Before they occur to cause failure, system failure. And now also to ensure optical vehicle performances. The relevant images you're having edge computing right here where it is indicating you have in-vehicle monitoring, which is basically by the installed devices such as the sensors. I explained them earlier. And then when they get this information, it's going to be processed using the mobile devices, and then it will provide instant notification via the handheld devices, for example, these phones, the laptops. And then for predictive analysis, we are seeing a lady that is carrying out analysis on data using the statistical approaches, as we can very well see the graphs indicating, representing the statistics and the data coming from the vehicle as well. The related works, we are having one, the mechanical systems and signal processing as one of the paper we reviewed, and the main focus of their project was regarding the predictive maintenance. The models that they build, you have the deep learning models, the recurrent neural networks, and the deep Boltzmann machine, deep belief networks, and the convolutional networks as well, neural networks as well. They didn't implement any ensemble learning, and they didn't have any XAI techniques. The challenge or the computational issues they were addressing were the noisy and the complex conditions. Then the other paper was about the predictive analytics as a service for the vehicle health monitoring using edge computing. Their project mainly was focusing on edge computing, which involved building models such as artificial neural networks, the k nearest neighbors, and ensemble learning of the artificial neural networks and the k nearest neighbor. So for them, they implemented the ensemble learning techniques, and then they didn't have any XAI techniques implemented, and the issues that they incurred were latency. The problem statements. The problem statement, basically, we are looking at the black box nature of the existing models. We are looking at the complex and noisy conditions that hinder the training of the traditional physics models. We're looking at the installation and production costs of sensors, which is also a hurdle in this situation as well. Then our main objective is obviously to implement an explainable machine learning technique for predictive car engine monitoring. And the other objectives are one, we are looking at implementing explainability, that is using Lime and Sharp. We are looking at addressing latency issues that is basically using edge computing, leveraging noise and then the complex patterns that affect training of the traditional models, and as well as improving vehicle reliability. Moving on to our contributions of this research one, explainability using Lyman Sharp basically to improve, to provide transparency of the models, ensemble learning for purposes of enhancing the generalization and reducing overfitting for better performance. Then implementing boosting models as well. Those are some of our contributions of this research. Then our methodology, we very well started. We started off with data acquisition. We downloaded our dataset from the Mendeley. From the Mendeley data, it was labeled the Hyundai car maintenance data type. We went on to do some pre-processing on the data, whereby we did imputation, filling in the missing values with the mean values. We also did some data encoding, where we had a variable that was in which was of an object data type. So we had to encode it to binary, to numeric data. We wanted to split our data into the training, testing, and validation. The purposes of splitting this data one, the training data was used for the learning process, whereby we had to go on and train our model using the training data, which was a 70%. Now the testing data was for purposes of model evaluation and testing the generalization ability of the model. The generalization ability is how accurately a model performs on unseen data. Then for validation data, it was well for fine-tuning and model selection. And fine-tuning is basically adjusting some parameters to optimize the performance of of the model. Went on to evaluate our performance, the model performance using precision. Precision basically captures or it measures how accurate the positive predictions of the model are. Then the recall, um, the recall mainly it measures how accurately a model captures the positive instances of the dataset. And both of these approaches are used when the false positives are greater than the true positives. And then we had the F1 score as well, which is basically the harmonic mean between the recall and then the precision. And it is best used when you're dealing with binary classifications. And since our issue was our project is regarding binary classifications, well, it was the best fit for us. And then the accuracy accurately measures the overall correct predictions of both the true positives and the true positives and the true negatives of the model. Yeah. Moving on to the models, we went on to build some the models and then train them. For those that were not best fit, we went on to do some hyperparameter tuning on them, and then we went on to do training again. Let's move on. Our exploratory data analysis results. One, we had the heat map, and for the issues of the heat map, we had the x-axis and the y-axis, whereby all features on the x-axis are similar to those on the y-axis. We have the engine temperature, brake pad thickness, tire pressure, maintenance type, and anomaly indication. That is the same thing that happens on on the x-axis. And then we had three colors mainly. We had the thick blue or the dark blue, which indicates a self-correlation between the features. We had a light blue, which indicates the positive correlation. And then our highest positive correlation was a 0.0588. And it was between the maintenance type and then tire pressure. Then our highest negative correlation, which was in the faint, let's call it faint blue, uh, over negative 0.00322236. It was between maintenance type and anomaly indicator. Then moving on to our scatter plot, which was indicating it was plotted between the engine temperature against the brake pad thickness. We have our key, which is indicating zero, blue for zero, meaning it is an absence of an anomaly. Then one, which is orange, indicating the presence of an anomaly. So we are seeing an even distribution and an implication that there is no outlier, since most of our values are between the 80 degrees centigrade and 100. Most of them are in between that, an implication that we don't have any outlier. And but when you look at the brake pad thickness scale, it is between 6 and 12. All of our values are enclosed inside there. And another implication that there are no outliers. So we're having an even distribution of both the absence and presence of an anomaly. Then our dataset description, as I said earlier on, we got it from the Mendeley data. One, it was the name is the Hyundai car maintenance dataset. It had 1,100 entries, and it had 5 features, 4 of which were integer data types, and then one which was an object data type, which we encoded later on to the numeric as well. Our target variable, which was the anomaly indication, it had 551 ones and 549 zeros. We didn't have, yeah. The models we implemented, the reason as to why we implemented some of these models, one, the main reason is because the literature we reviewed had suggested these models, so we went on to first follow that literature. But then narrowing down to other reasons, the k-nearest neighbor is best fit for small data sets. And as you can see earlier on, I said our data set had 1,100 entries. So the k-nearest neighbor would serve the best for such a data set. The support vector machines are usually used in complicated domains where we have a clear margin. So an implication that they are for classification. So since our project is a classification project, we went on to implement the vector machines. For ensemble learning, which involves combining the predictions of various models or different models for purposes of improving the accuracy and the robustness of the models, we went on to implement that. And it is best fit for reducing overfitting and enhancing the generalization ability of the models. Now, for boosting models basically it encompasses combining several weak learners to come up with a better learner. And it usually provides the best state of art for most domains. That's why we went on to implement it in our project as well. And it is also good at handling the bias and variances when dealing with machine learning. One of the architectures we happen to present in our paper is one. We have the artificial neural network architecture right here, which is having 3 layers. That is the input layer, the hidden layer, and the output layer. The hidden layer and the output layer, we are seeing that each of these layers has nodes, and the nodes within the same layer are not connected to each other, but they are connected to all nodes in the other layers. Now, our input layer, we are seeing an input variable labeled x, which is input to input layer to the input layer. Now, the input layer has several nodes, but only 4 are represented. The other ellipses represent the other corresponding nodes. Now, the interconnection between the nodes represents the weights, which weights are adjusted during the training process. And then the hidden layer is the one which carries out the complex computations or transformations on the input variables. Now, which transformed inputs are passed on to the output layer. Now we are seeing a function labeled hx on the output layer, which is responsible for computing the overall or the final output of this model. Let's go on to the other. These are some of our results. As I explained earlier on, the reasons why we implemented some these models, and then we use these evaluation metrics. Our nearest neighbor had the best performance. As I said, it is best fit for smaller data sets, and then for classification purposes, it had the best accuracy of 0.63118. Then its precision, remember I said precision measures how accurate the positive predictions of a model are of 0.566, the recall, capturing the positive instances in a dataset of 0.477, and then the F1 score, which is the harmonic mean of the precision and the recall of 0.4678. This deep Boltzmann machine and the DBM models, we tested them using the test accuracy and the test loss. Moving on to the XAI techniques. One, we have LIME, which is a local interpretable model, agonistic explainability. It is a very flexible XAI technique because it applies to a wide range of data. It can deal with numeric data, text data, image data, video data. It is very, very flexible. And two, it provides a benchmark for model debugging, an implication that you can know when a model is likely to fail or to perform right. And the main literature behind the LIME XAI technique is that it highlights the most, it works by highlighting the most influential feature towards model prediction. For SHARP as well is known as the sharply additive explainability, and for it works by highlighting all the features that what contribute to model prediction. And then it provides a greater insight into feature importance, whereby it explains how these features interact to do what? To to give the overall output of all the model prediction. Then the other thing is that for sharp is consistent in such a way that when you have a decrease in a value or in a value of the feature, you will as well have a decrease in the value of the sharp, or you have a decrease in the sharp value. So it does not work in the reverse way, whereby the feature decreases, then you're seeing an increase in the sharp value. It doesn't work that way. Then the other thing, the other best thing of dealing with Sharp is that Sharp provides two things. It has the global and the local explanation for model performance, whereby the global we mean it explains how each feature affects the overall model prediction, and then for local it explains how each feature affects the individual model predictions. Now let's go on to look at the predictions made by that. Let's go on to look at the predictions, the explanations for each technique. We are seeing the red line in the red bar in the line graph, which is for engine temperature, and it is less than 85.03 degrees centigrade. It is the red indicates the positive contribution, and then green indicates the negative contribution, and the negative contributions of brake pad thickness, and it is less or equal to 9.144, and then for tire pressure it is between 30.0.55 and 32.88. So an implication that this model relies on the lower values of the brake pad thickness and the tire pressure, while relying on the high value of engine temperature to predict the class 1 variable, or the class 1. Let's take it for that. Yes, now when you move on to the sharp has the x-axis and the y-axis, whereby the x-axis it has the sharp values on the x-axis, and then the y-axis it has the feature values. Now it has a line, or it has a key which indicates for the pink indicates the high values of the feature, and then blue indicates the low values of the feature. For engine temperature, we are seeing the pink is greatly spread towards the positive, an implication that the positive it provides the greatest positive contribution towards the model prediction, unlike for the tire pressure and brake pad thickness, which are spread to the left, and the high values are spread to the left, an implication that they contribute negatively towards the prediction. So it still sums up to the fact that the model relies on the low values of the tire pressure and brake pad thickness, while taking in consideration the high value of engine temperature to make the overall prediction. Then the conclusions of our research, we find out that our explainability greatly reduces the black box nature of explainability greatly reduces the black box nature of models. As we said earlier on, some reason as to why we carry the general reasons for carrying out explainability is one, transparency, which provides an explanation of how models come up with the results. Two is improving trust, more so if you're dealing with such sensitive issues, automotives, medical. Yeah, it improves trust in models. Then the other thing is regulatory compliance. We carry out explainability to fit the standards set by the operations of organizations that lead us. Then two is for error handling and model improvement. As I said earlier on, they provide benchmarks for model debugging. So when you know the model is likely to fail at this time, you can go on to what? To adjust, and so that you come up with the overall better performance. Then we as well went on to say to conclude that when you do predictive maintenance, obviously the reliability of the vehicle will rise to a reasonable figure. Then it also provides a basis for recommending the maintenance type on performing informed decisions when taking your vehicles for checkups or perform maintenance. Then the limitations of our research, it was a challenge to integrating the models into the existing systems. We had overfitting issues with the models. Then also handling categorical data was a bit a hurdle before we came to it. Now the recommendations one, we recommend that people go on to try out cross validation instead of using only the split and the split and the splitting approach. Then they should also go on to implement multiple XAI techniques, and then integrating knowledge experts, for example, engineers when dealing with side projects, and then applying multiple ensemble learnings to leverage noise and complex conditions. Our acknowledgements go straight to Mr. Dr. Galiwango Marvin, Department of Computer Science, Makerere University, and then some of our references are those. Thank you so much.